Hello and welcome to my talk. It's going to be on concentrate non-malleable codes in a split-state model. This is joint work with Divesh Aggarwal. We are both from National University of Singapore. Hey, let's start with the brief introduction to non-malleable codes. So it's a notion defined by Dziembowski, Pietrzak, and Weeks in 2010. The idea is as follows. We've got a message. The message gets encoded. There's a code word now. And then comes the evil adversary and tampers with the code word. We get some code word prime. And as a result, we get a message prime. Now, the question is how message and message prime are related. And the security requires that either message prime is equal to the message, or if that's not going to happen, then we expect that message prime is completely unrelated to the message. In other words, either adversary preserved the message or he overrode the code word and destroyed the message. In particular, the following example should not be possible. So changing original message into message plus one, that should not be possible. So any partial information about the message should not be possible to preserve. First of all, notice that the adversary has to have limited power. In particular, he can't do the following. He can't decode, add one, and re-encode again, because that results in the message being message plus one, which should not be possible. What are the common limitations of adversary? Well, there's quite a few classes. This is not the exhaustive list. The first one was independent bit tampering. This is from the original paper. In independent bit tampering, the adversary is deciding whether to keep, flip, set to 0 or set to 1 each bit of the code word. He does it independently for the bits. He doesn't see the bit 1 when tampering bit 2, for example. The other class is bounded depth circuits. We have the code word and adversary is applying some bounded depth circuit to tamper with it. Bounded locality, that's adversary is applying some function with bounded input or bounded output or both localities bounded. Bounded degree polynomial, that's self-explanatory, and one of the most popular classes is split state, if not the most popular. What's split state? Well, we've got a code word. We cut it in half. That gives us left state and right state. Now, adversary will tamper each state independently. What it means is that when adversary is tampering with the left state, he does not see the right state, and the right adversary does not see the left state. The adversaries agreed on the strategy. They share some common randomness, all that stuff. It's just when the tampering happens, I just tamper left state without seeing right state, and then I tamper right state without seeing left state. And combined left prime and right prime gives me new code word prime. Why do we care about split state? That's a good question. Well, first of all, as we discussed earlier, we have to limit the adversary somehow. And split state is very wide and natural class for which things are still possible. There's no limit on the computational complexity of tampering on each state. It's arbitrary tampering. It's just the only requirement is that the tampering happens independently on the states. So this is very natural and very strong class. It immediately gives 2 out of 2 non-malleable secret sharing, and it has a lot of applications as a tool for building other things. So first of all, it can be used to build non-malleable codes in other models, in other interesting classes. In particular, the first 3 papers, small depth circuits, local tampering, and decision tree adversaries, In all those three papers, the idea is to use the to-split state as a building block. Also, continuous non-malleable codes use split state as a building block. What are the other applications? Well, we can use them in non-malleable secret sharing. The ADN OPRL blah blah uses it as a building block. There are connections with privacy amplifications. There are connections with non-malleable commitments. Okay, now let's introduce non-malleable reduction. That's a notion by Aggarwal, Dodiskazana, and me. Once again, a brief restatement of the non-malleable code. So we got the adversary from some class F, and we can restate the security notion in the following way. So message prime is some function of message, and that function should be trivial. So either identity that corresponds to preserving the message, or a constant function that corresponds to completely deleting the message. Well, we can easily think about generalization of this notion, and that's exactly non-malleable reduction. So instead of requiring that G is in a trivial class, we require that G is from some family G. This is a reduction from F to G. We denote it with the arrow. G does not have to be a subclass of F. Obviously, we would like to have some non-trivial reductions, so G should be somewhat easier to handle than F. What are the properties of non-malleable reductions? Why are we interested in them? First of all, well, it's strictly speaking the generalization of non-malleable codes. Non-malleable code can be represented as a reduction. So non-malleable code against F is a reduction from F to the trivial class NM. NM contains only identity and constant functions. The other very important property is composition. If we have two reductions from F to G and from G to H, then we can just compose the encodings, and that gives us reduction from F to H. Obviously, if both reductions are constant rate, then the composition is also constant rate, which will be useful later on. Okay, let's talk about ADKO, what we showed in that paper. We showed the reduction from split state to look ahead and forgetful tampering in a constant rate. So once again, what are the classes? The split state was, we had two states, each state is tampered separately. To look ahead looks somewhat similar. We've got two states, but then each state is cut into multiple pieces of memory. On the picture right now, there are two pieces. We will be using three pieces later on, but let's focus on two right now. So what happens is the states are tampered separately, as in split state. And then on top of that, adversary tampers the memory parts in kind of look ahead chronological order. So he tampers the first state just based on a first state. When he tampers the second state, he knows the second state and the first state. When he tampers the third state, it's depending on a third state, second state, and first state, and so on. So when he tampers the third state, he does not know, first piece of the memory, he does not know the second piece yet. When he tampers the second piece, he does not know the third state, and so on. So that's to look ahead. What's forgetful, yeah, the picture is the same. We've got those pieces of memory. And now the adversary can pick one piece and completely delete it. So he lost the information from that piece of memory. But in return, he can do whatever he wants with the remaining pieces. So there is no split state anymore, there's nothing. He just takes all the other pieces of memory, processes them together, and outputs the code word. Also, in that paper, we showed a reduction from to look ahead and forgetful to trivial class. So basically, we showed the non-malleable code. Sadly, Xin Li found a bug in the proof. So the whole thing works on the plausible conjecture that the lemma is correct, but we don't know how to prove it. Which creates a gap. Basically, we don't have this part. Okay, what's our contribution? First of all, we give a new bootstrapping technique that allows us to give the constant rate construction of an MC against to look ahead and forgetful. And then that combines with the previous slide fills up that gap on the second part of the slide. So that gives the non-malleable codes in split-state tampering with a constant rate and negligible error. One thing that has to be mentioned at this point is that Xin Li gave non-malleable code that's constant rate, but that only works for a constant error. So that's sadly not sufficient for cryptographic application. All right, let's look into the construction. So the main building block is ADL, that's non-malleable codes from additive combinatorics. And what ADL is, it's a non-malleable code with very bad rate, but excellent to-source properties. First of all, it's augmented, so that's the equivalent of being strong in extractors. So like after the tampering, on top of output of the tampering, I can give you one of the states and you still can't retrieve the original message. That is assuming you did not preserve it. If you change the message, I can give you one of the states on top of that and you still can't retrieve the original message. That's augmented. It has excellent leakage resilience properties because the outer layer of ADL is just inner product. So that inherits the leakage resilient properties of the inner product. And then it's also super. What's super? That means that if the coding is valid and the message has changed, then the whole tampered code word does not hide any information about the original message. So it's not only that the coding can't retrieve the information, but also the whole code word doesn't hold any information anymore. We do use all those properties in the proof. Okay, so what's the construction? The construction is two states, the upper and the lower state. There are three pieces of memory in each state, right, as in to look ahead. And yeah, the tampering order is from left to right. So the left piece of the memory is tampered first, then the middle part while knowing the left part, then the right part while knowing everything else. Okay, so how do we construct it? First of all, let's just pick X and Y uniformly at random. And let's denote the output of the extraction, like the two-source extraction on X and Y as Z. Then we pick A and B, such that extraction on A and B plus Z is equal to the message that we want to encode. Don't worry about Z star for a second. I will explain what's Z star in a moment. For now, think of it as just Z. And once we have that, all that's left is using ADL. So the first left part of the memory, that's ADL. And what it encodes is just checks on X, Y, Z, A, and B. Okay, that's the construction. Let's go through some tampering scenarios. Again, that's the construction. And scenario one, adversary keeps the ADL. So that's the first piece of the memory he's tampering with. He's tampering with L and only sees L. He's tampering with R and only sees R. What if he preserved everything? Well, then he preserved the checks. If he preserved the checks, then he can't change anything else, so the message will be preserved. All good. Scenario 2, again, our construction, and scenario 2 is, well, what if he tried to mess with L and R? Well, then by the properties of ADL and non-malleable codes in general, he had lost the checks. And here the properties of ADL are quite crucial. So if he lost the checks, then it seems like he should be able to do whatever he wants, but there's a small catch. So what are the checks? It's a series of seeds and checks on each memory piece independently. So it's a seed and check on X, seed and check on Y, seed and check on A, seed and check on B. And what's the check on Z, which will be quite crucial here? It's just a small prefix of Z. Now, the problem is that the adversary has to commit to the small prefix of Z right now. That follows from the look-ahead properties of look-ahead, look-ahead tampering. So he does not see X and Y, and he has to commit to the prefix of Z right now. Okay, but then, short intermission, I can explain what's the Z star now. Well, Z star is just a suffix of Z. It's whatever's left of Z, except of that prefix that's used in checks. That's done for the independence purposes. Okay, but the adversary committed to the prefix of Z prime. Okay, and now we've got two scenarios. Either X prime and Y prime carry information about X and Y, or they don't. If they do carry enough information about X and Y, then Z prime has to be uniform, because X prime and Y prime are high entropic. But if it's uniform, then it's not going to fit the prefix adversary committed earlier on. And by properties of inner product of ADL, that prefix he committed to is completely independent of the actual Z prime we will get. Here. So there's that check will not be fulfilled. The code word will be invalid. Okay, what's the scenario 2? The scenario 2 is that X prime and Y prime did not carry enough information about X and Y. But then they don't carry enough information about Z. And thus, we don't know what Z star. If we don't know Z star, we don't know the message, right? So that kind of concludes the overview of look-ahead tampering. And now, we only discussed about look-ahead. We did not discuss the forgetful. So how to add the forgetful? Well, the whole idea of forgetful is if we lose one piece of the memory, then all the remaining pieces should not reveal the original message. And that's exactly 6 out of 6 secret sharing. Now let's look again at the construction. If I say forget X, then I forgot the extraction output. Then I forgot Z, I don't know what's Z star, and I lost message. That's good. The same with Y. What if I forget B? Well, then I forgot the extraction of A and B, I forgot the message. That's cool. So if I forget any of X, Y, A, and B, I'm done. And by the way, this is why Z star is just a suffix of Z, because L and R still preserve a little bit of information about Z. And we don't want L and R to be used to recreate a little bit of information about Z and recreate the message. So this is why we're using Z star. Okay, so we good if we forget any of X, Y, A, or B. The problem is if we forget L and R, that's irrelevant because, well, X, Y, A, and B fully determine the message. So the idea is quite simple. Let's split x into x1 plus x2 and y into y1 plus y2. And yeah, let's spread them this way. And now if I forget the first part of the memory, so I forgot L and x1, that means I forgot x, that means I forgot z star, I forgot the message. If I forgot A and B, it's the same reasoning as before. If I forgot x2 or y2, again, the same reasoning. So now suddenly it's 6 out of 6 secret sharing. The analysis of this construction is identical to the analysis of the previous construction. We just split it into 2 steps for readability of the paper. Great, that will be all. Thank you for listening, and yeah, bye bye.